Good day, everyone. I'm Kathleen Jan Benavista, and I'll be your first reporter for this water resource engineering subject. So, let's discuss about descriptive and quantitative hydrology. So, before we proceed to that topic, let's have first review on hydrology because this topic um, discusses the thorough study about hydrology. So let's have define hydrology. Hydrology can be defined as a study of water. It can be defined as the science that deals with the space-time characteristics of the quantity and the quality of waters of the earth, encompassing their occurrence, movement, distribution, circulation, storage, exploration, development, and management. So simply, these are the characteristics are determined by the relation of the water to the earth. So now let's have hydrological cycle. Water cycle, also called hydrologic cycle, it is a cycle that involves the continuous circulation of water in the Earth atmosphere system. So as you can see at the picture, this is the illustration of the water cycle, and we have here the important processes that we can have in our water cycle. We have the percolation, evaporation, transpiration, condensation, and precipitation. I believe we have a lot of knowledge about hydrological cycle and hydrology from our previous subjects. So I hope you can understand it well. So what is the importance of hydrology? The hydrologic cycle is important because it is how water reaches plants, animals, and us humans. And beside from producing and providing people, animals, and plants with water, it also moves things like nutrients, pathogens, and sediments in and out in our aquatic environment. So the most important uses of hydrology are flood control, drought mitigation, water supply, pollution control, urban and industrial development, design of hydraulic works, agricultural production, land conservation, environmental impact assessment, land use change, navigation, recreation, and fisheries. So, as we can see, it is all about water. So, before we proceed to our very topic, which is the descriptive and quantitative hydrology, let's first discuss what is descriptive and quantitative data so that you can have a little idea on how or what is our topic will going through. So descriptive research, it is a quantitative research method that attempts to collect quantifiable information for statistical analysis of the population sample. So applying it to our topic in hydrology, it is simply a method that collects data or information for statistical analysis of, for example, precipitation, runoff, or other stuff that involves the study of water. So first, we have here hydrograph analysis. I believe um, it is tackled before in our previous subjects. So I believe you have a little idea about this. So what is hydrograph? Hydrograph, it is a graph that's showing the rate of flow or discharge versus time past a specific point in a river or other channel or conduit carrying flow. And also it can refer to a graph showing the volume of water reaching to a particular outfall or the location in the sewerage network. So I have here an example of a hydrograph. So this is the hydrograph. So we have here discharge for the y-axis and for the x-axis, we have time. It is a matter of hours, days, or weeks. So before, in our previous subjects, we are tasked to draw a hydrograph, and this is what it looks like. So we have our rising limb, lag, storm flow, base flow, precipitation, peak, and also our receding limb. Next, we have here, aside from hydrograph analysis, we have estimating volume runoff. So we have the formula of R is equal to P minus L minus G, where our R here is the direct runoff, our P is precipitation, our L is basin recharge, and our G is the groundwater accretion. So runoff coefficients. So in the design of storm drains and small water control projects, runoff volume is commonly assumed to be percentage of rainfall. So we have also the um, formula for our runoff. We have R is equal to K multiplied by P, where our K, it is the runoff coefficient for various surfaces. So in solving this um, rainfall or runoff volume for the percentage of rainfall, we have different types of surfaces. So also we have different values for our case. So for example, in our single houses, the K value of it is 0.20. For garden apartments, we have K is equal to 0.30. Commercial and industrial, K is equal to 0.9. For parks, K is equal to 0.05 to 0.30. And for our asphalt or concrete pavement, K is equal to 0.85 to 1.0. So take note for that in solving our R. So we have different types of K. That's why we need to identify first what type of surface we have in our problem. Next, we have infiltration. Infiltration, it is a movement of water through the soil surface and into the soil. So, we have infiltration capacity. It is a infiltration capacity of a soil at any time is the maximum rate at which water enter the soil. And also infiltration rate, it is the rate at which water actually enters the soil during the storm, and it must be equal to the infiltration capacity or the rainfall rate. Next, we have infiltration indices are used to compute the estimate of the volume of runoff from large areas. So also we have formula for this. W is equal to quantity of P minus R over T, where our W is the index or loss rate, and our R is also direct runoff, P is our precipitation, and T, it is our duration of rainfall in hours. Next, we have rainfall runoff correlations. So the simplest rainfall runoff correlation is a plot average rainfall versus resulting runoff. So typically, the relation is slightly curved, indicating an increasing percentage of runoff at the higher rainfalls. Next, we have long period runoff relations. It may be necessary to estimate a monthly or annual stream flow from the precipitation data. Such estimates may be needed to extend a short record of stream flow or to forecast future runoff for planning reservoir information. So, forecasts for several months in advance are feasible only when precipitation is um, larger in the form of snow that remains on the ground during the winter months. So the most accurate method of estimating long-term runoff is probably as a summation of storm runoff amounts, but such a procedure is only feasible if computers are employed. Next, we have hydrographs of catchment outflow. So if a rainfall were applied at a constant rate to an impervious surface, the runoff from the surface would eventually reach a rate equal to the rate of rainfall. So the time required to reach this equilibrium is the time of concentration, which is Tc. And for small impervious areas, one may assume that if rain persists at a uniform rate for a period at least as long as our time of concentration, the peak of the runoff will equal to the rate of the rainfall. So we have here the basic rational formula for our hydrographs of catchment outflow. We have Mulvaney's equation. So we have two different types of equation here. So the first is um, Q sub B is equal to I multiplied by A sub D, where our Q sub B it is the peak rate of runoff in acre inches per hour. Our I here is the intensity of the rainfall in inches per hour, and our A sub D it is the catchment area in acres. Note that 1 acre inches per hour is equal to 1.008 cubic feet per second. So our area here must not be or greater than 10 acres. And also if we are using cubic meters per second in our Q sub B, our I also is in millimeters, and in area is in hectares. So our formula that we'll be using is Q sub B is equal to I multiplied by A sub D over 360. So take note for that, the different um, units. For small plots without defined channels and from which runoff occurs as laminar overland flow, time to equilibrium in minutes is given by, so we have here, time to equilibrium is equal to 41B L LO raised to the power of 1/3 over I raised to the power of 2/3, where our LO here is equal to length of the overland flow in feet, and the coefficient B is given by, so in this formula we can have B is equal to 0.0007 I plus C sub R over SO raised to the power of 1/3. So our SO here is the slope of the surface, and our C sub R is the retardance coefficient. Next, we have unit hydrographs. So if two identical rainfalls could occur over a catchment with identical conditions prior to the rain, the hydrographs of runoff from the two storms would be expected to be the same. So this is the basis of our unit hydrograph concept. So a unit hydrograph is a hydrograph with a volume of 1 inches or 25 millimeters of the direct runoff resulting from a rainstorm and specific duration and a real pattern. So here we can have the picture beside our unit hydrograph. So as you can see, it is the same from the first illustration that I gave to you a while ago. So last, we have here synthetic unit hydrograph. So only if flow records and recording rainfall are available can unit hydrographs be derived. Many watersheds are ungauged. Consequently, various methods have been proposed and used for deriving unit hydrographs based on geometric and topographic characteristics of the watershed. So this is the illustration of our synthetic hydrograph graphic features. So we have our A, C, and E, where is our A is the point of rise, C is the peak, and E is the endpoint of the recession. So that's all for my report for this morning. I hope you learned something new from our discussion. I believe it is informative. And thank you so much for listening and watching this video. Thank you. Bye.